design of shear walls.
Correct.
I'll just present my screen.
Yes.
Okay, we are working on the same model that we were
Hmm.
working on in the previous classes.
Yes.
Right. We had done the design of frame elements. Okay,
Hmm.
if you have the run and the if you have run the model for analysis and design,
Hmm.
okay, we can view the analysis, the design results by going to concrete frame design,
Hmm.
display design info.
Hmm.
Okay, there are many ways where, like, we can see the total longitudinal reinforcing. Okay, this was not designed. I'll just run the design. Then we can see the rebar percentages. We can see the shear reinforcing. Okay, and the PMM ratios, the interaction ratios, and so on.
All right.
All right, and we had left the design of shear walls.
Hmm.
Okay, so the first thing we'll do today is the design for shear walls.
Hmm.
Right now, in shear wall design, we need to assign some labels like piers and spandrels
Okay.
in the shear wall. Right. So whatever vertical element of the shear wall is there, those need to be assigned as piers.
Hmm.
Okay, and whatever in this case that there is no opening in the shear wall.
Hmm.
Right. So everything here will be defined as piers.
Hmm.
Fine. If there is some opening in the shear wall, say if there is a window,
Yeah.
or say there is a
Utility opening.
say, like, yeah, utility opening or anything like that. In that case, the portion of the shear wall above the opening is to be given as a spandrel label. Okay, it is designed as a spandrel,
Okay.
and the vertical elements are designed as your piers. Okay, so these are the different design output views that are available for the frame designs. Okay, you can
As we
explore
will
that.
run, how to come to this menu?
Okay, this menu is actually go to the concrete frame design.
Hmm.
This button over here.
Hmm.
Okay, just beside this button there is an arrow button. You can
Yes.
press on that. Okay, you have this display design info,
Okay.
right? And in display design info, you have a lot of options like total longitudinal
Hmm.
reinforcing. You have total rebar percentage.
Hmm.
You can view it in the form of rebar percentage as well,
Yeah, that we
right?
saw last time.
Yeah, you can view the column interaction ratios also,
Hmm.
right? Then you have your beam column capacity ratios for those junctions over there, right?
Hmm.
And you can view column beam capacity ratios, that is the inverse, and general reinforcement details. You can view that. Okay, right? General reinforcement details, it will give you the total, like say your shear reinforcements are shown as AV, and the major and the sorry the flexural reinforcement is shown as 1028. Like
Why
that is
it
also
is
shown.
shear reinforcement? Why it is showing two values, 716 to 3040?
Actually, there is your column has the major axis and the minor axis,
Hmm.
so it shows two values, one for the major axis and another for the minor axis. So for while designing, we'll go with the higher value, whichever is
Okay.
available. Okay,
Okay.
and
This much
then
more.
yeah, then we can also identify the failures here, what kind of failures the frame elements are undergoing. Like if you have PMM failure, means you're having your interaction failure,
Hmm.
and if you have PMM and V, that means you're having both interaction as well as shear
Shear.
failure, right?
Okay.
So you can also view the beam design, display beam design over here in the form of charts or a diagram. Okay, in this fashion, this can be used for making reports or
This is
even
giving
for
envelopes
identifying.
for each beam. Positive and
Yeah,
negative envelope
yes,
for
yes,
both.
yes, 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 correct. Okay, so this is that, right? And then okay, now we'll go to the this can be explored on your own also. Okay,
Hmm.
I'll not go into too much in depth on that.
Hmm.
Okay, now what I'll do is I'll go come for the shear walls.
Hmm.
Okay, before we start with the shear wall design, we need to define some piers and spandrels. In this case, for the first case, I'll only show for the piers. Okay, now if you go to the define menu, you can see that your fifth option is pier labels, right? We'll define pier labels over here. So we'll define say P1, then P2, right? P3 and P4. Okay. Now what I'm going to do is I'll select all the shear walls over here. So the first shear wall here is in grid 4. So sorry, grid A. So I'll go to the elevation view, set elevation view. I'll go to grid A, and I'll select this shear wall, and I'll assign. I'll go to shell. You see, can see that I have not unlocked the model. Okay,
Okay.
and these design options, they can be
Hmm.
even worked on without unlocking the model.
Sure.
Okay, so you have this P1,
Hmm.
then this will be in say grid 1. So I'll open the elevation for grid 1. I'll keep it as P2. Then the next wall is along grid 7. So I'll open the elevation, go to grid 7, select them, make this P3, and the third one will be long grid. Okay, 7 is done, A is done. This is remaining. This is grid G. So grid G has a wall. I'll give it as and name it as P4. Okay.
This whole wall we are putting as a pier,
Yeah, single pier. Okay,
single
for
pier.
better optimization, you can also, you know,
Make it
give
story wise.
different PL. Yeah, yeah. Story wise, you can give different PL labels. I'm just
Hmm.
can see that here. What happens? You get the results story wise also.
Okay.
Okay, see you can see here,
Hmm.
and to
What
view the
result it is
report,
giving?
it's giving the reinforcement ratio. No, not the reinforcement ratio. It's giving the rebar area.
Okay.
Okay, for the seismic design, and here you can see that your the like your pier is like divided into top and bottom.
Hmm.
Okay, like station location is top and bottom, means the top means the upper flow. Okay, and
Okay.
bottom is
Upper
the
and
lower
lower.
flow. Yeah, upper and the low. So top, this is the rebar area required, and for bottom this is the rebar area required, right? And here it's showing that there is some design inadequacy. Okay, the pier fails in flexure or PMM interaction. So your pier has to be increased in
Thickness.
like the thickness has to be increased, right?
Thickness of the wall
And
has to be increased.
yes, yes. And this area is actually the area result is given for the entire length of the wall, correct? So
Okay.
your 6 meter wall has this much area of steel, right? So per meter, you can find out the uh,
Divided
area
by
of
6.
rebar per meter also by dividing it.
Hmm.
And you can divide it equally on both sides of the wall,
Okay.
right? So this is how the
It
and
is
your
giving us a double mash, no?
yeah, 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 double mesh. Okay, and
Top
your
mash and bottom mash. But top and bottom, you
yeah,
are saying they are as
no,
per
top
as per
and
the
bottom
story.
is actually those are the stations, right?
Okay.
Your actually maximum forces are there at the top and the bottom of the like where the floors are intersecting. Okay,
So this is
so
only
there
giving for 6 meter. We have choose the wall for whole say 24 meters wall.
no, 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 no. That is for the entire thing. But your this top and bottom is the height, right? And 6 meter is the width of the wall. Actually, if you just check here,
Okay,
I'll
six
just
meter is
go
width
to
of the
the
wall. Understood.
yeah,
Understood.
6 meter
Clear.
is the width of the wall.
Width of the
So
wall.
that yeah, it is giving the details for the entire width of the wall. Okay, and your shear rebars are also displayed here over here. You can see the shear design here. Okay, in shear design, it's failing. Okay, so it is OS. It's giving a error. Sorry, overstressed message over here.
Okay.
So normally, what happens if it's designed, then you get the rebar, the shear
Area
rebar
with an
area over
mm
here.
square per meter.
Yeah, in mm square per meter. Right. Okay, and your boundary element checks are also performed here. Okay,
So whatever is the critical
so
value coming, we give it uniform we convert into mesh for the same, and we'll
yes,
detail it
yes,
accordingly.
yes. Here you actually you have your boundary element also over here. Okay, you can see that your boundary element here has a 3 meters over here. Okay, it is considering the entire thing as a boundary element.
Okay.
Okay, 3 meters on the left, 3 meters on the right means your entire uh, shear wall is designed
Hmm.
as a boundary element.
Hmm.
So you can change that length of the boundary element also from the design overrides. Okay, that can be seen from here. You can go to your view device preferences. Okay, now say like we did for the frames, there
Hmm.
is this. You can change the design preferences for the shear wall as well. Okay, you can change the rebar material from here.
Hmm.
Okay, the and the shear material will remain the same,
Hmm.
and your different parameters are given here, right? These are most more or less this will remain same, and your say there are some overrides also over here. You can check those overrides. So before I check those overrides, I need to select all the shear walls first. Otherwise, that menu will not be active. So I'll select the shear wall. I'll go to this shear wall design. Okay, view device peer overrides. Okay, here now here you have your uh, over here you have the peer section type. It is designed as a uniform reinforcing, or you can also go for simplified TNC, tension and compression type of design. Okay, so here now you can you see that you're getting your db1 left bottom. You can increase the size. Okay, the thickness at the top can be increased if you wish to increase that. Okay, so you can play with the parameters over here for your shear wall design with the simplified TNC. Okay. Then you have your okay. These are the peer sections. You can define your peer sections prior to the design. All right, and you can also select the design combinations. Say you have your predefined design combinations. You can just select them and move it here, and delete all the previous and remove all the previous
Hmm.
the
Auto
automatically
generated.
generated combinations. Okay, so you can explore this over here. Okay, and the different uh, design output results also are visible here. Like you have peer similar to the frames, we have the
Hmm.
peer longitudinal reinforcing. You can view the peer reinforcing ratios also. Okay, I'll just run it once so that we can see the results. Okay, you have the peer reinforcing ratios displayed here. You can see the peer shear reinforcing. Okay, you can see here it is being displayed in mm square per meter. Then your peer edge or boundary zone widths, you can check here. Your boundary zones are shown over here.
Okay.
Okay, for the boundary elements. Okay, then we don't have a spandrel over here, so that is not being shown. So for a spandrel also it is similar. What needs to be done is okay, I'll just delete the design results and I'll just show for one case where there is a spandrel. Okay, for a spandrel there has to be an opening over here. So say I delete these two components. Okay, I'll unlock the model first.
Hmm.
Yeah, I delete these two shells from here. Okay, so now we have an opening, right? And for the opening, the portion of the wall above the opening, this portion will be now designed as a spandrel.
Okay.
Okay. So what I'll do now, I'll first define a spandrel. I'll go to the define menu, click on spandrels, and there is a predefined spandrel over here. Okay. So I'll now assign the spandrel label to this shell. So spandrel label S1. Okay, I'll just right click over here to check whether it has a peer label or not. It has a peer label. So from here, from this menu also, I can make this peer label as none.
Okay.
Okay, or you can just select them and go to assign, go to shell, uh, peer labels, and make this none. Okay, now I'll select these shells from here and go to share all design.
So why this spandrel is made in a different way than PS? What is the difference between
Because
this?
your uh, shear wall design normally has it normally has axial force and moments along two directions for
Hmm.
designing. Okay,
Hmm.
so major action is like similar to that of a column.
Hmm.
Okay, but whereas in case of spandrel, it is designed in the form of a beam.
Okay,
Okay,
flexural acceleration.
a thick beam.
Okay.
Okay, right. So that is the major difference over here
Okay.
between
So if I would
pier
have
and a
defined,
spandrel.
if would have assigned everything as spandrel, then it would
Yeah.
not have been right.
Yeah, it would, you'll definitely get some result, but that
Hmm.
result won't be correct.
All right.
So now I have defined the spandrel over here. I'll I'll see the spandrel overrides over here. Now here you can see the spandrel overrides. You have your length as 3 meters. Okay, and your thickness in the left is 300 mm, depth in the left is 1500 mm. Okay, and your cover bottom left is 150. You can change the cover over here. Okay, as per the design requirements. Then you have the slab width to the left and the slab width to the right. Okay, the thickness, then similarly the thickness in the right side, depth in the right side, the cover at the right side. All right, these things can be changed as per the design requirements.
Okay.
Okay, uh, same thing can be done for peers also. Okay, when you enter the peer overrides, when you enter the peer overrides over here,
Hmm.
you can change the cover and all that from here
Correct.
as well.
Hmm.
Okay, and edge design also, the edge distances also can be varied over here, right? Okay, so I'll run the analysis and we can then see the results. Okay, here in this case for the spandrel design, you will get the top and the bottom V bar for the spandrel, and you'll get your shear reinforcing, and you will also get your X diagonal reinforcement also. Okay,
Bracing type.
as per the IS 13920, we need a X shaped rebars over here in the coupling beam. Actually, this is a coupling beam kind of a
Hmm.
thing.
Hmm.
Okay, so we need X shaped rebars in this as well. So that result also will be available. Okay, I'll start the design check for the pier and the spandrel. Okay, now here first we are getting the pier longitudinal reinforcing area. We need to turn this off and go to the spandrel. So we'll go to display design info and we'll see the spandrel longitudinal reinforcing. Okay, so here you can see 1514 square. This is the you can just right click on it and open the report and view what results have been displayed. Right. So here we have the this now here the station location changes from unlike the peer design report, it changes from top to left and right.
Hmm.
Okay. So left your rebar area requirement is 1515 and right it is 1514. Okay, your reinforcement percentage is also displayed here. Your combinations, the critical combinations are displayed, right? So this is the design for the top reinforcement, and this is the design for the bottom reinforcement.
Hmm.
Okay, and your spandrel shear design is also shown here. Okay, this is the vertical, this is the vertical shear stirrups that is required. Okay, and horizontal, how much uh, you need horizontal area you need for shear, and your diagonal shear rebar is also displayed here. Okay, now these are the results in the report form. You can get it in the graphical user interface as well. You can go to the design output. You can check for spandrel shear reinforcing. You'll get the spandrel shear reinforcement.
Hmm.
Then you can check the spandrel diagonal shear reinforcing. It will give you the diagonal shear reinforcing as well. Okay, and similar to the frame design output, we can also identify what failures are there. Okay,
Hmm.
so we can view that in the form of in the form of graphical user interface. Wherever we have failure,
Okay.
that will be shown here. Okay.
So we have to assign spandrel both above and below the opening, nearby the
Uh,
openings.
no, actually, the portion of the say the portion of the wall that is below the opening,
Hmm.
that can be assigned as a pier.
Okay.
There is no problem with that.
Okay.
But say there are multiple openings.
Hmm.
There is one opening on top as
Correct.
well. So in that case, say there is an opening over here.
Hmm.
I'll just unlock. Say there is an opening over here.
Hmm.
Okay. In that case, your
Then
spandrel
store
will be this portion as well as the top portion.
top portion also.
Yeah.
Top till what place, till what height we should go?
Actually, that is normally till the next
Story.
till your next story, or say till the next opening also.
Okay.
Okay. Now say if you have yeah, in this case there's a story over here, so you can take it up to the story as well,
Okay.
or you can design if you wish to design say from here, like in this case you we have a uh, like if you just take it up to the story,
Hmm.
up to this story, we'll just have this much depth of the spandrel.
Hmm.
So we can extend this from here to the next story as well.
All right.
We can design this entire portion
This
as a
entire
spandrel.
portion is spent.
Yeah. So in that case, you might get some optimized results. So that
About
depends on the user.
yeah, which is on left and
Which
to the right, they can be merged
yeah,
in the peer geometry.
yeah, they will be part of the peers.
Okay.
Okay. And
So.
one more thing needs to be
Hmm.
kept in mind while designing shear walls is that your meshing has to be proper. Okay, in that, like in the sense, say uh, this I have a 4x4 mesh over here.
Hmm.
Okay, so the wall in the story above this, that should also have a 4x4 mesh. Okay, so
Okay.
that all the nodes intersect at one point. So if I now divide this into two parts,
But
and
if
one
say
node is
that is T shape or C shape or L shape, then there will be you have to discretize only those T say flange section as separately and web section separately, like that.
yes, yes, yes.
Okay.
Okay, but your like the nodes, they all have to meet at one point. We
Hmm.
can't like if I say divide this into two now,
Hmm.
this node will now be falling on the body of this element over here.
Hmm.
So in that case, there will be an error. It is a FEM solver, so we need to keep in mind how we discretize FEM elements.
Hmm.
So see, it's similar thing has to be done here,
Hmm.
and even for the slabs, like your slab meshing and your what do you say, your wall meshing, they also need to coincide. The nodes need to coincide.
Okay.
Okay. Otherwise, there will be discrepancy in the results. So you might get some absurd values,
Hmm.
right? So while working with shear walls, this is the most important thing
Hmm.
that needs to be kept in mind. Or otherwise, what can be done if you don't want to go into too much of headache for meshing? It's always easy if you just model a frame element of none property over here
Okay.
and divide it into equal parts.
Okay.
All right. So what happens is that if we have a joint anywhere in
Hmm.
this on the slab,
Hmm.
so in ETABS, what happens is the floor meshing that is done internally, it
Hmm.
automatically picks up the joints and creates a node over there.
Okay.
Okay. So if you have a say a frame element of none property
Hmm.
drawn over here,
Hmm.
right, and you divide it into say
For
four equal
parts.
parts.
Hmm.
Yeah. So there will be a joint over there,
It will be creating
and
nodes. Yes,
yes,
automatically.
and your meshing will also
Be done
automatically
through
be
that node.
proper.
Hmm.
Yeah.
Understood.
Okay. So in that and in that case, what happens? Even if the meshing is not done, your what do you say uh, the K factor for the walls are also taken as absurd property.
Hmm.
Okay, like if the meshing is not done proper, your effective length also increases over here,
Hmm.
and then your wall design will also give some absurd values.
Correct.
Okay, so these things need to be kept in mind while
Hmm.
working with shear walls.
Sure.
Okay,
Similarly, for core
so
also, we'll make a core is like four elements connected. If I am
yeah,
saying
four
in between.
elements connected. Correct, correct. Even core shear walls are similar.
Hmm.
Okay, or your lift core,
Hmm.
that is also
Core or
similar.
inner
And
shear walls, or
yes, inner shear
junctions.
walls
Yeah.
also. Yeah, and even at the junction, you need to keep in mind your meshing is proper. The nodes, they connect
Hmm.
properly.
Okay.
Okay, all your meshes, they should connect at the corner points,
Okay.
right?
As we are
And
seeing displacement of story, can displacement of shear walls be seen as at one as say a
no, no, no,
line
no, no,
diagram?
no, no,
We
no, no.
have
I
to see
think
plate by plate, element by element. We have to see.
we actually get to see the if we need to see the displacement of the shear wall only. Actually, now it's a combined system, no? So you'll get to see the displacement of the entire building.
Hmm.
Individually, if you need to check, you can always view the deflected shape for the for your say for your lateral loads. Okay, and you can go to the no the joints over here and check on the displacement values.
Now, if we
Okay,
say we
otherwise,
are doing a research problem and we are seeing, say, what is the effect of certain material, I'm
mm, mm,
giving us a certain shape to it, to my shear
mm,
wall, and
mm,
then I'm changing the material of the shear wall or openings in the shear wall. And I want to
mm,
see as a overall behavior of the shear wall, how much it gets displaced. So I have to take
okay.
plate by plate element results and then I have to combine them and then see the result. Or can it have?
Oh, you can actually view it in this fashion also. Like, say, I'm turning on the EQX,
Hmm.
okay, the lateral load. So, what happens is like your displacements are shown over here. Okay, so at the corner points, you can see the displacement results over here.
Hmm.
Okay, and
No, I was thinking as
you
you
want.
have defined them as a pier or you have defined them as a spectral. So it
Hmm.
does it create certain properties so that as we are seeing a very good diagram of the
Okay,
story
okay,
bits
okay, okay,
in
okay,
that way
okay,
it can
okay.
be seen.
Okay, I think that can be seen. I'll have to check.
All right.
Maybe that also can be seen in the form of peers.
Hmm.
But what here, let's just see whether it's
This is
possible or
for
not.
whole story. Yeah, you see if that
Yeah,
is
this is
possible.
actually
Let
for
us
the whole story.
know. Yeah.
Okay, like say, mm, okay, EQX, and we have. Okay, just wait a minute. Let's see. Mm, you can see the forces. Okay, you can see the forces over here, but mm, there might be a way. I'll just check and let you know on that.
Sure. Sure.
Okay. For individual like for special things like that, I'll just
Yeah,
need to
that will be
check
okay.
and tell.
Sure. No
Okay.
issues. No issues.
Because since we are getting peer, we might be able to get
Hmm.
those results also.
Yeah.
Yeah. Okay. So this is how we design
Hmm.
how we design shear walls.
Hmm.
Okay, in ETABS.
Correct.
Now, next thing what we'll do is we'll check the steel design also.
Hmm.
Okay, how it is done. Steel modeling is similar to whatever we have done already.
Okay.
Okay. Only thing is that your materials and frame sections will be different.
Hmm.
So here we'll go to the define menu. You can see your materials over here.
Hmm.
I'll unlock the model first. We'll go to the define menu. We'll go to the material properties. We'll go to add new material, and here we have predefined steel material. Okay, for India region. Okay, and we have two types of materials here: Fe250 and Fe345. If there are some other grades like say Fe3110 or something like that, we can always go to user,
Hmm.
okay, and define our type of steel,
Hmm.
or say some other grades which
Correct.
are not predefined here. Okay, the material properties can all be changed over here.
All
Okay,
right.
and we'll define something here, and next will be the definition of section properties. So we'll go to your frame sections, right? We have predefined member properties.
Hmm.
There are some predefined member libraries
Correct.
in ETABS.
Hmm.
Okay, we can go to import new properties. Okay, and steel, there are some I sections, channel sections. Then we have box sections, pipe sections. Okay, there are some steel composite sections also, but steel composite sections need to be defined by ourselves. Okay, so steel I sections. Now we have AISC library over here. We have ArcelorMittal. Then we have European sections. We also have the Indian sections over here. Okay, we have from India we have Indian General Steel, and we have Tata Steel.
Fantastic. Yeah.
Okay, so Indian for the Indian sections, the I sections, the
Correct.
ISMBs, ISLBs. Okay,
Correct.
all are predefined here.
Hmm.
Okay, we can use that, and I'll just select any one, and we'll see the section properties also. Okay, now for seeing the section properties, we'll go to modify show property.
All right.
Yeah, here we go. Now here we have the all the depths and the thicknesses and the widths have been predefined here
Hmm.
as it is. We can also convert it to user defined and change the
Okay.
sizes as per our requirements.
Hmm.
Okay, and for steel sections, we can also make the use of our section designer for say having some special shapes like
Correct.
uh, you know star shaped columns or
Hmm.
some other typical sections. Okay, we can always go to
Built up
section
sections.
designer.
Yeah.
Yeah, for built up sections also, yeah, and plate girders also we can also do that.
Hmm.
Base material here has to be taken as Fe345 or whatever is the steel property, and design type in that case will be general steel section. Okay, and in the section designer, as we had done for that L-shaped section, RCC section. Okay, here we have some predefined I sections, channel sections, P sections. Okay, then angle sections are there.
Hmm.
Okay, we can now from here we can use the replicate command, or change. You can change the dimension of this angle section by right clicking over here and going to the the geometry portion, and you can change the height, the width, and the flange thicknesses. Okay, fillet radius as per the design requirements, right? And we can say replicate that and make
Hmm.
a built up kind of a column.
Correct.
Okay,
We can
so
rotate,
this thing
replicate.
can
Yeah.
be, yeah, we can replicate it, and we can create different types of sections.
Closed section,
Okay,
back to back
yeah,
sections.
yeah. Back to back sections, or say battened columns, laced
Hmm.
columns,
Laced columns.
or we can have even your what to say star shaped
Hmm.
columns. There are different column sections that can be created using the section designer.
Hmm.
Okay, so This can be explored on your own. Okay,
Sure.
I'm not going to deep in this, otherwise it
Mm.
take up a lot of time.
Mm.
Okay.
Here also modifiers are same as we had seen in concrete. Section
Property
modifiers.
modifiers. Yeah, that is the same thing. Okay, you can define it here, or you can select it separately and define it. Okay, as per your thing. Like if it is, if I model this as a, actually what happens is in steel it is like the same section can be used as a column as well as a beam,
Beam.
right? So it is better not to use this table over here,
Okay.
and first create the model geometry using the sections, and then define the property modifiers externally.
Generally, what modifiers comes up in steel sections? Like in
Steel
concrete, we are
sections,
seeing
we take it as one. There is no
there is generally
limitation.
no changes. No?
No changes.
In
Okay,
concrete,
but
we are doing point 0.7, point 0.3,
yeah,
but in
yeah,
steel,
point
we
0.7, 0.35. Still, it is the same.
okay.
Okay, but maybe if any properties need to be modified,
Hmm.
that it's better to do it after creation of the after creating the model geometry.
Okay.
Okay.
And is there a provision for connection also here, or what is it? What is it considering the connection between two steel members? Welded one,
Uh, uh, if you uh, if you just model it, it will take it up as a rigid connection.
rigid
Okay.
connection.
Yeah, and for the moment releases, we need to apply them externally.
Okay.
Okay,
Okay.
like whatever moment releases are there,
Hmm.
that needs to be defined externally. So if it's a semi-rigid connection, you can find out your from the m theta curve, whatever is the type of the connection. If it's semi-rigid, some partial fixity can be given.
Okay.
Okay, so like if I say select this beam,
Hmm.
okay, I can go to assign frame releases or partial fixity. All right.
Hmm.
So in this case, if I say release this, okay. So what happens is here now the moment per unit rotation is taken as 0. So I can, after ticking this, I can, for a semi-rigid connection, I can give some value as per the empirical
Stiffness can.
charts of IS 800. Yeah, we can have some stiffness in the joints as well.
Hmm.
Okay. So that can be modeled by using releases of partial fixity. Okay. So it is actually the same thing, like modeling. Only the definition part is a little different.
Hmm.
Okay. And say if you want to like I had shown definition of a, predefined property, you can also have a user defined steel section. Okay. In that case, only thing is I need to go to add new property. Then the same window will come up. I'll just click on the I section or whatever section is there. Now here I can modify it as per my requirements. Okay, you can see the changes in this window. Okay, and your section properties also, it can be viewed over here. Okay, your moment of inertias and product of inertias, everything will be visible here, CG and all that. Okay.
Hmm.
And your steel design is also the same, only like modeling is similar to your concrete, like RCC. Okay, the only the definition part is different. And while after finalizing the geometry, your connections need to be defined. Like uh, say if it is a fully moment release connection, we need to go and assign releases. Okay, if it's a semi-rigid, then as per the joint stiffness, we need to assign partial flexibilities, right? And your only thing is that after you finish the analysis, you need to come here. This is the steel frame design button. Okay, and to the right of this, there is a small arrow, right? Over here, you can, after you run the analysis, your uh, this
These
window will
options
be
will go.
activated.
Yeah.
Okay, you can start the design check
Hmm.
and check the adequacy of your steel members. Okay, all other processes are same, like your base shear amplification factor and everything, all the processes that we did, like your response reduction. function definition, everything will be the same. Okay, only your definition will be different. Okay, your connection definition is will again be different, and your this design button is different. Okay, this menu can be explored. Okay, for your like say for you can change your design overrides like we did for the uh, RCC for the RCC frames and the shear walls. Okay, so what I'll do is I'll just take one beam over here. I'll assign uh, steel property just for your you know
Mm.
uh, just for your viewing purpose. I'll just make one steel beam over here. Okay, and say I'll assign the frame releases. Okay, I'll give some values here. Okay, okay. Now I'll select this. I'll select this beam, and we'll see the revised preference view or revised preferences. Okay, so your framing type is SMF. That is a special moment frame. Okay, this is as per your IS 800 or 13920. Okay, okay. You have the ductile frame, that is the
Correct.
special moment frame.
Mm.
Okay, we have the ordinary moment frame also.
Mm.
Okay, then eccentrically braced frames and all that, those are also available. Different types of frame designs are available.
Okay.
Okay, and your design for your design, seismic design. Okay, the
I.
importance factor, I factor here can be defined. The zone factor can be changed from here.
Mm.
Okay, this is for the this will be used for the design, not for the
Okay.
analysis.
Okay.
Okay, then
Then for
your
this we have to give beam by beam or entire selection
no,
we
no,
can
no.
give it like
The actually your
preferences
design
are for
preference
all. All.
for all.
Okay.
Okay, on the overrides are for the individual elements.
Understood.
Okay, you can set your what do you say, your deflection limits also over here.
Okay.
Okay, light super dead load plus
L
light
by
load as
120,
120.
L by 120.
Yeah, yeah. L by 360 and all that. Okay,
Understood.
then total camber also can also be kept over here. Then the demand capacity ratio limit is automatically taken as 0.95. Okay, that also can be modified, right? So this is for the preferences. Then for the overrides also. Okay, here we have the current design section as ISWB 550. Okay, so if there are, say now you run a design and your design fails for this particular section. Okay, say
Failing will be
ISWB
shown by
550.
red.
Yeah, red.
Okay.
So I'll just run the design, then
Mm.
we can view it. Okay, so now here we can see that the color is shown as a cyan, so it is safe. Okay, but say if it is unsafe, okay, we can always change the design section also.
There
Okay,
are maybe 5 6 colors shown below.
yeah,
You-
yeah, below here there are 5 6 colors. It shows the range of the uh, demand capacity ratio. Okay,
More than one is
so
not.
yeah, it is less than zero point 0.5,
Mm.
so it is safe, right? And if you have a failure, it will normally be above 1, so it will be red in color. Okay, so say if your member fails in design, we can always go to the overrides and change the section from
Section.
the overrides.
Okay.
Yeah, if there are 2 or 3 sections, we can always
Mm.
change it from here and check the
It will
demand
calculate.
capacity ratio again. Yeah, it will automatically change.
And it
But
will have to again run. Model has to again
But
be built.
yeah, we can check whether it is safe or not, but it's always better to run,
Hmm.
right? Because your analysis is for the previous section.
Hmm.
Okay, so and here also we have various uh, you know various options over here in this overrides button. Okay, you can like whatever we had seen, the deflection limits and all that, and it also calculates the unbraced length ratio. Okay, in the major and the minor direction, the unbraced length ratio for torsional buckling. Okay, then effective lengths are also calculated. Effective length factors are calculated. Then the C1, CMZ, CMY factors are also calculated automatically. Okay, but when there is a large structure, okay, while designing, there might be some uh, there if there is any discrepancy, you can always check and modify that. That freedom is given to the user.
He can overwrite.
Yeah, you can always override that. Okay. Okay, so there are various things here. We can also manually calculate these factors and give them as overrides, and it will automatically run the design for whatever changes we have done. Okay, these are the strength combinations. You can also check for deflection. Okay, the deflection ratios here are also given.
Okay.
This is also in the form of demand capacity ratio,
Hmm.
right? Whatever is the limit by whatever is the deflection,
Hmm.
the real time deflection. Okay,
This
and for
counts
the
for
report,
concrete beams also. The similar
uh,
kind of manager, report manager.
similar kind of thing for deflection.
Yeah, for like strength combinations separately, service combinations separately. That was
That
not there in
I
concrete.
think I think your for concrete it might not be there. Okay, for steel it is more important.
Hmm.
Okay, you can see here
Yeah, it
that will
is.
not be available for your
Hmm.
concrete. Okay, for steel it is there.
Hmm.
Okay, uh, then you can see the reports from here. If you go to the details, okay, you can see the report. You can see uh, the section properties, the material properties over here. All are calculated over here. Okay, and all the codal checks as per the clauses. The clause numbers are also given. Okay, all like your uh, the demand capacity ratio from the PMM equation that is there in the IS 800 code. Okay, then your K factors, L factors, and the KL by R ratios all are calculated and shown here. Okay, so all these reports can be a very good exercise for the BTech or the MTech students for manually verifying the results
Yes.
of the design.
Hmm.
Okay, from ETABS, right? This can be a very good exercise for them. So
Are there any verification examples kind of thing you also given? The ETAPS help
that
module or somewhere?
the ETABS help module, you won't get that. Uh, you won't get that, but you can always do it on your own.
Okay. Like
Okay.
in STAD and etc., they are giving certain verification modules or verification example solutions also in their help
Mhm.
section itself. If some kind of reference module is also available, where
No,
certain code examples,
we have a very big and
knowledge base.
comprehensive we have a very big and comprehensive manual over here also. I'll show you that manual now.
Okay.
Okay, there's this help button over here.
Hmm.
Okay, we can go to your documentation.
Hmm.
Right, in the documentation now you can view your license agreement and all that also, and there are some tutorials. Okay, introductory tutorial is there for ETABS. Okay, you can now here there are some small example models over here. Okay, if someone is a very new user, they can always
Hmm.
refer to this for creating a model.
Hmm. Okay,
Okay,
step by step
uh,
or model.
step by step, everything is given over here. Okay, for I think we have a concrete building over here, and the steel building is also there. Yeah, steel building is there, and a concrete building is there.
Okay.
Okay, then there is this. Then there are manuals. Okay, we have the analysis reference manual. This is the big comprehensive manual that I'm talking about. Here we have details of what are the different objects and elements. Like main modeling here is in the form of objects. Like we have the frame sections, frame objects, and all that. Okay. Then we have the shell objects and your like degrees of freedom, then joints. Everything is given here. Okay. Then your FEM uh, like FEM elements that are used, like the shell elements. Okay. Then plane elements. Okay. Then solid elements. Solid element actually is not a part of ETABS. It's part of SAP.
Okay.
Okay. So but that is also given in this reference manual. Okay. Then we have the link and the support element. We have seen I think I had shown a rigid link, how it is defined.
Weird link we kept for last. We could not
Okay,
see.
rigid link, I'll show that.
Mm.
Okay, then we have some advanced non-linear options also.
Mm.
Okay, like there are non-linear link definitions also. Okay, for defining dampers or for base isolators. Okay, then tendon objects. Okay, then the different functions, the load patterns.
Mm.
Okay, then your modal analysis. Everything is given in detail over here.
Okay.
If anyone is interested, like the uh, non-linear, time history analysis, then the non-linear static analysis in the form of pushover. Okay, everything here is mentioned. Okay, the geometric non-linearity, like the p delta effect. So this manual can be always viewed for clearing doubts. Okay, if that arises. Otherwise, we are always there.
Mm.
Okay, and then we have the lateral loads manual.
Okay, that is
Okay,
separate.
this is separate. This is actually your uh, this is the manual for the seismic load and the wind loads. Okay, the automatic wind loads that are there in the program.
Okay.
So you can see there are a lot of manuals over here, and
Mm.
even for various codes it is given.
Mm.
Okay, so you can always check each and every manual if there is any doubt.
Mm.
Okay,
That's
like
separately. Yeah.
yeah. Okay, so
Here verification is there, no? One uh, below in manuals there was one option of help
uh, steel
verification.
frame design.
Verification. Come below.
Yeah, verification. There are some small. I think it is available. Okay, we just check.
This verification
No,
log.
this is something different. This is something different.
Here examples are shown.
Here some examples are there. Like we have the static gravity load analysis. Okay,
Yeah,
see
correct.
here some small problems are there.
Yeah,
Okay, you can always compare the results and
yeah. This is one good
model
way
it and
to. Yeah, this is one good way to always check with
yeah,
small things.
yeah. Then we have dynamic analysis also over here.
Where we can do some hand calculations also, and then with
Yes,
those
yes,
hand
yes. I
calculations.
think your design examples are also there,
Okay, for
like we
main
had
code
stated.
must be there. Yeah,
Yeah, yeah. See, there are some design examples there as well.
correct.
Okay, so this can be used for practice as well as verification.
Yeah,
Okay, it is all there in the help,
yeah,
in
yeah,
the
yeah.
in the help and the ETABS documentation.
Yeah. Sometimes they give it their file also edb file also. I don't think so. That is there available.
That I think you can explore uh, the ETABS
Documentation
folder
folder. Yeah,
that is there in
documentation
C
folder.
drive. Okay,
Yeah.
there might be some models.
Yeah, some models
You
generally
can
they give when they give a verification
yeah
problem, they give
yeah.
the model also for the same
You
model.
can also check. You can also check the document whether the name of the model is specified there or not.
Hmm.
Okay.
We do that.
Uh, or else you can check in C drive in the computers and structures folder
Okay.
in ETABS in the ETABS folder. There might be some models,
Sure.
some EDB files, which is there for verification.
Okay.
Okay. Okay. Now coming to this rigid link.
Yeah.
Okay, I'll unlock this model. So definition of rigid links. For rigid link definition, you go to section properties. Okay, and here we'll go to this third last link support properties.
Why here deck
Okay.
sections are given? Deck sections are generally used for bridges, no?
Oh, we this deck sections are actually for your composite floors.
Okay.
There we have that corrugated plates,
Okay.
right? And where the concrete filling is done, and
Hmm.
the beams are connected using shear studs. It's for
For
that.
the okay, they are deck sections.
For that's composite design.
Understood.
Okay, and here in section properties, we'll go to the third last option, link or support property.
Hmm.
We'll modify or show property here.
Hmm.
Now here in this rigid link, uh, the link property name, the link type. Now, as per your uh, the material properties and the dynamic properties also, we can have the different types of links over here. Okay, like this gap element. This is a non-linear element. Okay, where there is a gap between two structures.
Hmm.
Okay, or two components of a structure,
Hmm.
and then we have the different types of dampers over here that are defined. Okay, and these properties need to be taken the from the company's literature for whatever damping properties and all of that,
Okay.
and whatever non-linear properties they have.
Hmm.
Okay, so I'll not go into too much deep into this. There are a lot of options for non-linear analysis over here.
Hmm.
Now, for the definition of a rigid linear link, we'll select the link type as linear, and uh, uh, and we'll be taking all the directions u1, u2, and u3 translation as fixed. And similarly, we'll fix all the rotations, or we can just use fix all.
Hmm.
Okay. So in that case, we have now defined a rigid link.
Hmm.
Okay. So rigid link has been defined. Now we can use that for say now say like as I had earlier mentioned,
Hello.
a beam which is
Hello.
resting on a column.
हाँ जी.
Okay, having some offset.
हाँ जी.
Okay, say uh, say this beam now. Okay, this beam is being
हाँ
modeled
जी.
over here. Okay, it's
हाँ
supposed to
जी.
have an offset
हाँ जी. हाँ जी.
of say this beam. The edge of this beam is supposed to or say for this beam. Okay, the edge of the outer edge of this beam is supposed to be flushed with the outer face of the column. Okay, in that case, your member will not be able to transfer the forces
सर अभी मैं एक मीटिंग में
intrinsically.
था. मैं भी
Okay,
मैं
we
आपको
need to
थोड़ा सा
define a
समय देके बात
rigid
करूँ
link
तो ज़्यादा अच्छा रहेगा.
between the column center or the joint here
हाँ,
and the
श्योर
beam
श्योर, यू कैन
center
ऑलवेज
over
कम.
here.
आई एम अवेलेबल टुमारो.
Okay,
नहीं नहीं, सिविल ही है सर.
say this
मैंने
beam
नहीं
is
इकोसिस्टम
modeled
दिखाऊंगा, अभी मुझे कुछ चीज़ें अपग्रेड भी करवानी है, तो यू कैन
in this
ऑलवेज
fashion.
कम. दैट विल बी ग्रेट. यस सर, यस सर. सर यू कैन श्योर ऑलवेज कम. ठीक है सर. ऑलराइट सर.
Certain point. And I have 151. Oh, sorry. This will be okay. So if this is supposed to be having this column is I'll just check once. Column is 650.
Mm.
and the beam is 300.
Mm.
It's in the center, so 150 and 325. So it's having around, so 175 offset will be there in this particular element.
Mm.
Okay, and this will be along uh, two axis, along axis 2.
Okay.
Okay, so 175. Okay, so now this has transferred over here.
Mm.
Insertion point. Okay. Okay, I think it was there in the previous section, previous versions. In this version, this has been removed.
Okay. Previous
Okay.
versions, what could have been done?
What would have happened is like your this column point center would have been here.
Okay.
Okay.
Center
So
was
in that case, there would have been some gap, and that had to be
made with the rigid link.
modeled using a, yeah, with a rigid link.
Okay.
Okay, or say if you have a column of a very large depth.
Hmm.
Okay, in that case also for connecting the beam to the column, okay,
Center.
to the center of the column, we'll have to use rigid link.
Okay.
Okay,
Property of that rigid link will be null, I guess, and that
uh,
is just that
the
those nodes move together.
yes, yes, the property will actually not be null. It will be like it will be massless. Okay,
Hmm.
and it what it will do is it will transfer all the translations and the rotations
Hmm.
from one point to the other.
Other point. Okay.
Okay, so it's basically a connecting element.
Connecting element wherever two,
Yeah,
yeah, center
wherever
of
like
gravity
say
may
your
want to move together.
yeah, wherever your like the the beam center or and your column centers are not coinciding.
Hmm.
Okay, that has to be used there.
Okay.
Okay, okay. So I think that part is over now. Okay,
Hmm.
now we'll come to the wind load generation.
All right.
Okay, wind load generation was left out.
Hmm.
So for wind load generation, there are actually four ways by which we can apply wind loads.
Okay.
Okay. Uh, your first will be you can have a user defined wind load pattern
Hmm.
where you calculate all the forces manually and
Hmm.
apply them.
Hmm.
Okay, you can apply it in now. Before when you apply it, the ETABS module gives us two ways of application. One can be applied at the diaphragm, other it can be applied to the shell objects.
Okay.
Okay, so first thing what we'll do is we'll check for the diaphragm application. Okay,
Okay.
so here we need to define the wind loads. We'll go to the define button and go to the load pattern. Okay, so your load name will be say wind X, and the type will be wind.
Hmm.
Okay, now if say your autolateral load is none, so this becomes a kind of your user defined menu. Okay,
Okay.
so if you have say if you're designing an industrial structure,
Hmm.
or say you're having a sloping roof
Hmm.
somewhere.
Hmm.
So for designing for that, it's better to use this none type of window, where you calculate all the coefficients yourself, and the pressure has to be applied on the shells or on the frames.
Okay.
Okay, and next will be if you just take this IS 875 2015. Okay, and define a new load. Now go to modify lateral load. Okay, so here you can see that your winds will be applied. either by exposure from extents of diaphragms or exposure from shell objects.
Okay.
Okay. So now first thing we'll check the exposure from extent of diaphragms. This is a much easier method.
Because it will
Okay.
do separation story wise. At each story
Yeah.
level, it will apply
Yes.
directly.
Yes. 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 Okay. Now exposure height you can always change. Okay. You now in this case bottom story will not be base. It will be the first
Story
story.
one.
Yeah. Story 1 to story 12, and your now here we need to define the windward coefficient and the leeward
Lever
coefficient.
coefficient. Okay.
Okay, so as per IS 875, for a rectangular clad structure,
Mhm.
when there is a wind blowing, okay, so the face that is the windward face, it has a particular coefficient. The leeward face, that is at the opposite corner,
Mhm.
that has a coefficient, and the side walls also they have some coefficients.
Mhm.
Okay, so here in this menu, we will be defining the windward and the leeward coefficients only in this particular menu. For the side walls, it will be defined separately.
Mhm.
Okay. So now here, whatever coefficients are there, that need to be calculated and applied here. Now, mind that this coefficient will be the net coefficient. It won't only be the external coefficient.
Okay.
Okay. So your whatever internal coefficient is there, that net has to be calculated and applied here.
Okay.
Okay, and your basic wind speed needs to be
Mhm.
written here as per the
Understood.
IS code, as per the zone, as per the wind zone. Okay, you have the terrain
K1, K2,
category.
K3, K4 or factors.
Yeah, then we have importance factor as per the cyclonic region or not, whether it's cyclonic region or not. Then the risk coefficient, K1 factor, and the topography factor as per the for
Mm.
the as per the contour.
Okay.
Okay, and then there is another option of including parapet. Okay,
Okay.
now if I turn this button on, what happens is we can enter the height of the parapet. Say if we have 1.5 meter parapet or 1.25 meter ka parapet. Okay, and the wind load on that uh, particular wind load acting on the parapet of this particular height will automatically be applied on the diaphragm.
Okay.
Okay, the force as well as the moments. Okay, now
Or the top
one
story diaphragm.
yes, top story. Now one thing needs to be kept in mind here. This include parapet option can only be used when we don't have a mumpy floor or don't have a machine room floor.
Okay.
Okay, what the program does is it will take the highest
Highest
value of
point.
Z.
Yeah.
Yes, and it
Machine
will
room that will
calculate
only
the
take
parapet.
that much. Yeah.
So
Understood.
if we take a machine room, it will only take the wind load on the machine room parapet.
Mm.
Okay, so if we have a machine room, it's better to apply the forces and the moments separately on the frame elements. Okay,
Or we can model also the parapet. Otherwise, physically also.
yeah, we can model that. Okay, we
Physically
can
and
model that.
then
But
what?
in that case, you won't be able to use this exposure from the extent of diaphragm.
Hmm.
Okay, we'll
Okay.
have to use exposure from cell
Shell
objects.
objects. Yeah.
Yeah. Okay. So now I've defined this wind load.
Hmm.
Okay. And next will be now what I'll do is say I have defined the diaphragms, right? I'll
Hmm.
just check once.
Yeah.
Yeah,
You have.
diaphragms are defined. Okay. So now the next thing will be assign wind pressure coefficients. Okay. Now say your coefficients. Okay, we are defined for the windward and the leeward sides.
Hmm.
Okay. So for the other two sides, we can apply the coefficients from here.
Okay.
Okay. Say you have the whatever coefficients are there, we can apply it from here. But this will be for only for the shell load assignment. We're using it for the
Right.
shells.
Okay.
Okay. So now this is how we can apply the wind load in the form of a diaphragm.
Now, how to
Okay.
apply
Another
it now? Is it applied already? We have
yeah,
not
it is
assigned
applied.
it. No?
Yes, yes, yes. It is applied. It is an auto lateral load, so that will be
Okay.
applied. Okay,
Okay, this is
you can
already
check
done.
in the,
Yeah.
yeah, you can check in the load case also. A load case has been created over here for WX.
Okay.
Okay, okay. Now next will be your uh, application of the wind load for shell objects.
Hmm.
Okay, so before now we need shell objects in this empty place. Okay,
Okay.
in the periphery.
Hmm.
Okay, we need shell objects over here. Okay, so shell objects can be either modeled manually by using non-property shell objects. Okay, or else what we can do is there's an easy way. We can go to draw. Okay, draw auto draw cladding.
Okay.
Okay, you can use floats. Okay, or say you can select some objects and create. So okay, so you can see here your cladding is created. Okay, and if you right click on the cladding, what you can see here is that it is having none property.
All right.
Okay,
So it
so
is creating on the top also. No, top there is a floor.
no, no, top it is already there.
And the floor is already
Top,
there. Yes. Yes.
top we already have a slab.
Slab 150 thick. Yeah.
Yeah, we have a 150 thickness ka slab over there. Okay, and you can see it is from the
Not
first
from the
floor, not from the base.
base. Okay.
Okay,
Right.
so now we'll again go to define. We'll go to define load patterns. Okay, WX wind, modify lateral load. Okay, now say if someone needs to check
Which
for
is.
okay, now if say earlier we had done exposure from extent of diaphragms.
Mm-hmm.
Okay, now we if someone is doubtful whether the entire floor is getting the wind load or not, we can always check the wind directions and exposure widths from here. Okay, now here you can see that your table comes up. Okay, you can see the width of the diaphragm over here, the width and the depth of the diaphragm. These are the x and the y dimensions basically.
Okay.
Okay, and your actually here for while defining the wind loads. Okay, we need to say when we are said defining wx positive, we need to give 0 degree over here. Okay, and say when we are defining w
Vertically.
say yeah, we are having wx minus, we can
Minus
take it as
180.
180 degree.
Mm.
Okay, 180 degree, it will become opposite.
Oh, perfect. Yeah.
Okay, and see, we can always have user defined exposure width also. Okay, we can change the coordinates over here,
Yes.
the extent of the diaphragm, we can change that. Okay,
If
okay.
I create, say, kind of a purlin and rafter kind of structure, support truss
Mhm.
structure, will it create cladding in that direction also, say at 30 degrees, 45
No, no,
degrees?
no, 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 no.
That has to be
That
manually.
case, that has to, in that case, we'll need to define a wind load case
Mm.
having auto lateral load from the auto lateral load has to be none, and define the wind pressure as uniform load on shell or purlin, or as frame load on the purlin.
Okay.
Okay, that will be in the individual like load definitions.
Individual load definition at each
Yeah.
purlin we'll do it.
Yes. Yes. Okay. So next will be exposure from shell objects. So in that case, now you can see that all your things have become
No, it not
these things
needs
have become
CPI also in this case.
that will apply it from the shell load application.
Okay, at
I
that
opened the
place,
window. I just closed the window before
assignment to
that.
their CPs.
Yes, 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 yes.
Okay.
Okay. So here now I'll close this. Okay. So now what needs to be done is say this is wind x plus.
Hmm.
I'll just check once, which is the axis. Okay, this is x direction. So this is say wx plus. So what has to be done here? Now you need to select the cladding over here.
At shear wall, there is no cladding, no?
Shear wall also on top of that there is a cladding.
Okay, it
Okay,
is.
cladding actually it will not affect your analysis results.
Hmm.
It will just transfer the
Loads.
wind
Yeah.
forces. Yeah. So better way to select is just open the elevation. Okay, elevation A.
Mhm.
Okay, then select this entire thing over here. Even if frames are selected, that is not a problem. Okay,
Okay.
I'll go to assign. Okay, shell loads. Okay, here we have wind pressure coefficient.
All right.
Okay, so now coefficient CP, say for the windward side.
Correct.
Okay, now windward side, whatever coefficient you have,
Higher
say
coefficient.
0.8 or say 1.1, whatever coefficient is there, I'll apply that. Okay, now you can see here the coefficients have been applied.
Okay.
Okay,
So there, so many coefficients are applied, or what? At shape.
actually here what happens is here your shear wall is also selected. So what
Yeah.
can happen is you can deselect, since the shear wall is a shell object.
Already a shell
Okay,
object.
it's all, yeah, so it's already a shell object. What can be done is if the entire selection is already made, we can always deselect the
Deselect.
shear wall
Yeah.
and apply
Apply.
it on the cladding. Otherwise we'll have two times the wind load
Double
applied.
load. Yeah.
Yeah. Okay. So this is so we have defined for the, this is for the windward side. For the leeward side, we need to again go to the elevation.
Mm.
Okay, this will be G, elevation G. Okay, select everything. I'll again now I'll deselect the wall. Okay, now if I deselect the wall, everything will get deselected. So I'll need to deselect the shear wall.
We are in selection properties. You have
Even
to.
in selection, we have this deselect option.
Okay.
Okay, the same window will open for both the
Okay.
cases.
Same. I selected.
Yeah. So now say the this will be leeward side. Okay, for leeward,
It
say
looks
this
like
is
it is
0.
still selecting. It is not deselected.
No, it is deselected. The joints are only selected.
Okay. Joints are. Yeah, understood.
Yeah, joints no issue. Okay. So now we have say for the leeward side, I have applied it in the negative direction. Okay. So you can see here. Okay, negative means in the negative x-axis. Okay, or you can check from here also loads here. This is the windward side, and here we have for the leeward side.
Oh,
Okay.
correct.
Now for the sides also we can do the same. We can do the same exercise. Say we have this. This is now grid 1. Say this is 0.3. Okay. Apply. Okay. Now these directions can be changed by the positive or the negative sign.
Correct.
Okay. Similarly for for grid 7. Okay. So now the wind coefficients have all been applied.
Now,
Okay.
is the cladding
And
need just to be removed or can be there? In the
cladding can remain there since it is having none property. It will not,
effect.
affect the analysis results. Okay. So this is how you can apply the wind loads either from diaphragm or shell objects. Okay. In diaphragm, what happens? Your sides are taken as constant.
Okay.
Okay. Sides, whatever is there in the leeward, that will be taken as constant. Here we can change that.
Hmm.
Okay. And another method is, say, for your gust factor analysis.
Hmm.
Okay. For gust factor analysis, what can be done is your whatever gust factor is there for the structure, that needs to be calculated separately from the dynamic analysis result.
Hmm.
Okay, that needs to be done separately, say either manually or in an Excel sheet. Okay, and the force on each and every flow needs to be calculated in a tabular format, and we can insert that in this load pattern. Say I'll define a load pattern wx dynamic, and here it will be say wind. Okay, wait a second. Oh, wait. You have to come to user loads. Okay, searching for this user loads.
Mm.
So modify that, it becomes user load. Now we go to modify lateral load.
Mm.
Okay, so here we have, you can see here different stories are shown,
Yeah.
different diaphragms are shown. It is similar to the form, similar to
Yeah.
the diaphragm form.
Mm.
Okay, but only thing that is different here, that is we have fx, fy,
Forces
and fz.
we are providing.
MZ, yeah, and we have the ordinates. We can change the ordinates if we feel like, and whatever forces are, being tabulated from the gust factor analysis, that can be inserted here.
This will be
Okay,
applied as a point load.
no, this will be applied as actually it will be applied on the diaphragm.
Yeah, but not as a UDL. Huh? This is kilonewton it is taking, not kilonewton
No,
per
no,
meter.
no, no, no. It will be converted into a,
UDL.
but like, yeah, it will be converted into a UDL. Okay, by applying it on the diaphragm.
Okay.
Okay, in that case, what will have to be done is you'll have to calculate your area also. Okay,
Mm.
and apply.
Okay. Ordinate
Okay,
it is taking the diaphragm center, no?
yeah,
X ordinate, Y ordinate. Diaphragm is
yes,
36 by 36, so it is
yes,
taking center of that.
yes, yes.
Okay.
Okay. Now, in normal this in the normal wind load application, where we are assigning it in the extent of diaphragms, the vertical height is calculated by the story heights.
Okay.
Okay, so in that way, your wind load is being applied. But in this case, we are applying it as force. So
Okay.
your vertical height also needs to be multiplied, and we need to input this in the form of a force,
Force.
either force or moment, whatever is there.
Mm.
Okay, all right. So this is the method of applying loads using the gust factor.
Mm.
Okay. So this is the third method of wind load application, and the last method that I actually mentioned in the beginning. That is, if we define it as none.
First, yeah.
Yeah.
Okay.
Okay. Say Wx none. Okay. So in this method, what happens is we have a load pattern defined. Okay, which is of the type wind, but it doesn't have any subscribing port to it.
Mm.
In this case, what will happen? We can apply it as a form in the form of a frame load on say the frames, or we can apply it as a uniform shell load on the shells. Okay, so we'll go to assign. We'll go to the frame loads distributed. Now from this load pattern name menu, we can select WX none. Okay, even the autolateral loads, even in the autolateral loads also we can give some definition.
Mm.
Okay, you can give some user defined definitions also.
Mm.
Okay, so now say I'll be applying some loads in the x direction.
Mm.
Okay, so global x. We can also apply it in along the local axis.
If
Okay,
applied on shell, yeah.
yeah. So now the uniform load will be say 25 kilonewton per meter. Okay, so we have wind load applied in the form of UDL on the frame object. Okay, and this can particularly be used if you are modeling slope roofs with with
Okay.
rafters and purlins.
Mm.
Okay, there you can directly apply this wind load in the form of UDL on the purlins.
Mm.
Okay. Or else, if you are modeling the roof sheeting
Hmm.
in the form of a shell,
Hmm.
okay, in that case, you can always select that shell
Hmm.
and give shell loads on that.
Shallow definition, CP's definition.
No, no, no. If you're having a slope roof,
Hmm.
we need to define the wind load as none. Okay, the
Okay.
autolateral load will be none, and we need to apply it externally.
In sloped roof, it won't work as cladding we are working.
No, no, no. It won't work like that. So
Okay.
we'll go to again this assign. Okay, we'll
Shallow.
go to shell loads. We'll come to this uniform. Okay, we'll select the wind load none.
Whichever here.
Now, yeah. Now say if uh, you're normally to check your local axis, we'll
Hmm.
go to set display options.
Hmm.
Okay, and we'll go to other. Sorry, we'll go to object assignments. Okay, and local axis. We'll check which is the vertical local axis.
Hmm.
Okay, your vertical local axis is I think axis number 2. Sorry, no, axis number 3.
Hmm.
Okay, that is the vertical local axis.
Hmm.
So you select a shell and take it as local 3.
Okay.
If it is upward, we'll have to give it as negative, say negative 1.25
Hmm.
kilonewton per meter square. Okay, so we can see here.
Easier to give on rafters upward widths. On shell, rather it is little.
No, okay, shells actually no, even when we have inclined rafters,
Hmm.
right? You will have to use the local axis.
That also relaxes.
Yeah, you'll have to use the local axis when you're working on any inclined object.
Any.
Okay, yeah, any inclined object. Otherwise, you can use it. You can use the gravity direction and give it as positive or negative. In that
Hmm.
case, you'll only have the vertical component.
Hmm.
Okay,
For horizontal, we need to use local axis.
yeah, horizontal. You'll have to take
Oh.
local one axis and apply the horizontal.
Hmm.
Okay, so this is the fourth method of application of wind load. Okay, so we have total four methods. First was uh, automatic generation of wind loads through extent
Diagrams.
of diaphragm. Second was through the shell objects by creating autocladding.
Hmm.
Okay, your third was the gust factor analysis using user load manual
Hmm.
from the autolateral loads, and the fourth is from by selecting none option from the autolateral loads and defining it externally.
Correct.
Okay, and your wind load combinations for design that can be defined manually, or you can always use the automatic load combinations for your design.
Hmm.
Okay, your automatic load combinations for design that will cater to your wind load analysis. Okay, only for your seismic we need to have some user load combinations.
For automatic combination, will it take both wind and earthquake? We generally do for one.
No, your
If
wind and
both,
earthquake
if both
means like,
definitions are there, it will
yeah,
generate
your
combinations for both
yes, both in separate combinations.
in separate
Yeah,
combinations, and then it will give
both in
us.
separate yes, it will give you the results.
Okay.
Okay, only thing being that your 30% combination in the seismic response in the orthogonal directions,
Hmm.
that load combination has to be defined
Manually.
separately. Okay. And earlier I had shown one thing in the load cases. Okay, for your combined response spectrum. Actually, this won't be a correct method of you know defining the lateral loads.
Okay.
Okay, because we need to combine the responses, not the accelerations.
Okay.
Okay, so in this case, what will happen is your accelerations will be combined.
Hmm.
Okay, but this can also be done if you want to do it for any particular project. Okay, like if you want to see the combination of different accelerations, what are the results. Okay,
Okay.
in that case, you can change the direction of your acceleration by going to the advanced uh, menu over here. Okay, the advanced button. You click on the advanced button, you can see the angle of the of your load.
Incidence.
You
Yeah.
can change, yeah, you can change the angle, say 180 degree, then it becomes opposite. Okay,
Mm.
not by changing the scale factor. If you turn the scale factor negative, you'll get an error.
Okay.
Okay, in response spectrum analysis, we cannot have a negative response
Mm.
spectrum curve, so that has to be positive. Okay, but direction can be changed from this angle. Okay, by changing the angle of the action of the vector. Okay, by this can be activated by turning on the advanced button. Okay.
Okay.
Today I think I'm going a little fast. It might
No,
be a
it's
little.
needed. No, it's needed. Also.
Okay, I have to complete a lot of things.
Yeah. Yeah.
Okay, so okay, now one more thing I think Mr. Tanmay had asked just to show how the different time history functions are loaded in this. Okay, so it is similar. Like we have, there are some previously predefined earthquake functions that are defined, that are available to the user. Okay, in ETABS. Okay, so for accessing that, we need to go to the define menu. Okay, and we'll have to go to the functions. Okay, so in functions we have two options. One is the response spectrum that we had seen earlier. Second is time history. Now in time history, there are a lot of predefined functions that we have here. Okay, we have sine function. Okay, so you can see how the sine. Okay, sorry, that's the rank. So I'll add a new function. You can see how the sine function is there. This can be used for the transient analysis and all that things. Okay, now we can convert it to user type also in the form of a graph. You can input your own values over here.
Mm.
Okay, and make your own graphs. Next, we have the sine type, we have cosine type, we have ramp type. Okay, ramp type can be used for your blast analysis
Strategies.
also,
Yeah. Impact.
or yeah. Then we have the sawtooth function. Okay, for machine foundation, sometimes it's
Mm.
required. Then we have triangular functions. Okay, this is also required for machine foundations. Okay, we have user periodic. Okay, now you can define your own periodic function over here,
Mm.
right? And your uh, graph will also be shown here,
Mm.
right? And the last thing is uh, from file.
Mm.
Okay, there are some predefined uh, time histories there in the library. Okay, so we'll go to add a new function. Okay, and say now I name this as say L Centro.
Mm.
Okay, and the file name will be we'll have to browse it from the library. Okay, so what we have to do now when this file opens, we'll have to go to uh, C drive
Mm.
where your uh, software has been installed.
Mm.
Okay, so uh, I'll go to C drive. Okay, program files, computers and structures, ETABS 22. Okay, now we have time history functions over here.
Okay.
Okay, this is the L Centro function.
Mm.
Okay, open. Okay, now we'll convert this. Now values and values will be in the time and function values. Okay, and we'll have to open the file and check once. We'll view the file. Okay, so it has crashed. We'll just
Mm. So it is taking G values versus time value. No?
Yeah,
So we can even create the files from other earthquake data, and then we
yeah,
can have our own file,
you
which are
can
not
you
of
can,
earthquake.
but it has to be in the text format. I'll just
Text format,
show
yeah.
you. Yeah, I'll
That
just
should
show how it is.
be.
How the function, how the text file is formatted.
Mm.
So same thing. We'll go to functions, time history. This will be from file, add new function, browse. We go to program files, computers and structures, ETABS 22, time history functions. There are various earthquakes,
Mm.
mainly in Northern America,
Mm.
or even somewhere in Japan also might be there. Some might be there from Japan, I don't know.
Send no,
Okay,
it's
El Centro.
yeah, yeah.
Okay, El Centro now, time and now this equal intervals has to be turned off. Then you can
Mm.
see the shape of the function. Okay, now we'll view the file.
It is crashing at that point.
Yeah, it's crashing. I think I'll just show the file externally. I think that will be
Mm. Open with Notepad. No?
yeah. You can check from Word also.
Okay.
Okay, so this is the format. Okay,
First
how
is
the
time step, what I'm
yeah.
understanding, and
I'll just
second is the acceleration, I guess.
opens in WordPad properly.
Mm.
We have the WordPad. Just have to check WordPad.
Notepad, if you open, it won't be showing that.
Yeah, WordPad. Okay. Notepad also, I think you'll not will not be able to view the headers.
Mm.
There are some headers over there.
Yeah, any text, any code editing pad, it will.
Yeah, we actually have the time values and the acceleration values.
Yeah,
So
generally
if
it
you
is
just
like this.
without the header, we won't be able to understand
Mm.
what is the time value and what is the acceleration value.
Accelerations are in negative also, so second column it was showing
Yeah, acceleration
values.
will be negative.
Negative and
Okay,
positive
but
both.
since this is in text format, like the values will look a little random.
Hmm. And that can be worked out then. If we have
Yeah.
these values, we can work it
So
out.
now for time history analysis, say you import the earthquake
File.
file from your. I'll open some other model. I think
Hmm.
during the presentation I might have made some problem there. Okay, functions, time history. One file.
Is it opened? That's why it's okay.
Okay, let's check. No, it's crashing. Okay, so normally this will open. Okay, and you can see the uh, how the values are represented.
Hmm. Otherwise, also a representation is coming in that graph form.
Yeah. Or we can check. You can also check the other earthquake functions that are available.
Hmm. So after this, do we need to make a combination for this also? TH plus
See,
X. Yeah.
if you carry out linear time
Hmm.
history analysis,
Hmm.
okay, it doesn't make much of a sense
Hmm.
because
Because accelerations are anyways in different direction.
yeah. So you in that case you don't have to have those combinations that
Hmm.
you know that we had already defined. But uh, like if you're having a time history function defined, it's always better to go for nonlinear analysis.
Hmm.
Okay, because you will have if you're designing only using time history functions, it will be absurd. You will get a lot of no,
Higher
you get a
values.
lot of yeah, you'll get a bulky structure
Yeah,
out of
because
that.
maximum acceleration it will give
Yeah, it
as
will
the
give the
critical
maximum
value.
acceleration.
Yeah,
That
for that.
response reduction
Yeah,
will not be there.
yeah.
So say I will check some other functions also. We have say
Already
Altadena. Okay, so we'll view the file. Think might be able to. Okay, I think there's some problem in the
this
time history.
volume. Yeah.
Yeah, yeah. Okay.
We can just maybe press OK without seeing the function.
Yeah, we can press OK and we can define the function. Okay, that will uh, that will be your definition function. Now, for your nonlinear analysis, you actually have to define your PMM hinges. Okay, then PMV hinges, then you MV hinges,
Okay.
like shear and moment hinges.
That is
Okay,
after the
for
analysis
beams.
has been done.
No, 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 no.
Hinge
That
is
has to be done prior to the analysis.
prior to
Okay,
the
you
analysis as per our guess where the hinge can form.
yeah, as per our guess. Okay, and so we also need to uh, you know give the reinforcement area. Okay, for the beams and your columns. For columns, it's automatically taking, but
Okay.
that is only for your uh, uh, generation of PMM curves. So whatever design values you get, that needs to be separately defined in your columns, in the column sections. Okay. In this case, in these values, okay, these values have to be as per the design. Okay. So we need to first have the linear analysis done, the
Hmm.
design done, and all the detailing done, and then we need to insert the values over here and here.
Hmm.
Okay,
Okay.
for this will be for the confinement, and this will be for the longitudinal rebars.
All right.
Okay, uh, so this has to be defined first for the columns.
Hmm.
Similarly, we need to define it for the beams. Earlier, when you open the modified show rebar form for the beams, you would have seen over here that the rebars here, reinforcement area overrides for ductile beams. Here,
Okay.
the rebar areas are taken as 0,
Hmm.
but we'll need to define the top bars, okay, and the bottom bars
All right.
over here.
As per the
Here,
linear
normally,
analysis.
now here you see normally MV hinges are formed at the ends.
Hmm.
So you can see the rebar areas are for the ends only.
Hmm.
Okay, so that this needs to be defined. Then we need to define, say the we need to define the uh, we need to define hinges. Okay,
That can be done from
for
the
that
line.
that can be done. Yeah, we need to select the columns.
Hmm.
Okay, and then go to frame. We can go to hinges.
Okay.
Okay, and here uh, now this hinge property can be auto hinge. Okay, can we can select the distance, add hinge. Now the hinge type can be selected from here as per the specifications. Okay, we have AC41. Okay,
Okay.
and so degree of freedom can be M2 and M3.
Hmm.
Okay, and the hinge table here, from the hinge table we can take the reinforcement concrete, like say for beams, or if you have beams we'll have these two degrees of freedom. If we have say columns, we'll also have PM2 M3. Okay, that will also be available. Okay, and p values that needs to be selected from the gravity or gravity or lateral.
Mm.
Okay, so these things we need to refer AC41.
Okay.
Okay, and do the nonlinear analysis. Right. Similarly, even pushover analysis can be done in ETABS. Okay,
Mm.
for that we need to first calculate the target displacement
Mm.
as per the relevant say schema or whatever ATC codes are there, or
Mm.
AST code also,
Mm.
and then we need to define a pushover load case.
Okay.
Okay, pushover load case will be nonlinear static.
Okay.
Okay, and nonlinear static, and then your load application will be displacement control.
Mm.
Okay, and your this will be the target displacement, right? And you can monitor your displacement at say the topmost floor, or topmost at say a corner joint or the middle joint of your topmost floor. Okay, so these nonlinear analysis options are very detailed and very comprehensive.
Mm.
It actually will actually first we you have to practice the linear analysis and the design and get a good grasp of that.
Mm.
Then we can delve into this.
Mm.
Okay, this itself will be you know
Yeah.
actually the analysis itself will take hours to run.
Yeah.
Your pushover analysis, if you have a very good workstation, it might complete in 1 hour.
Okay.
Okay, and if you have a time history analysis, if you and time history nonlinear analysis,
Mm.
that if you have a good, very good, robust workstation, it might take 3 to 4 hours or 5 hours also.
Mm.
Okay, so sometimes it might not even converge.
Mm. Correct.
Okay, so that nonlinear analysis itself is a very comprehensive topic,
Yes.
and that we urge everyone to do it on your own. And
Mm.
if you face any problems, you can always refer to us,
Yeah.
right? And go through the manuals properly.
Mm.
The manuals are there. It goes in a lot of detail.
Mm.
There are a lot of explanations that
Correct.
I might have missed in the lecture,
Mm.
that will be available in the manual. Okay,
Yes.
so I think I have covered more or less
Yeah.
everything.
Maximum. Yeah.
If anything is missing, you can always try on your own and get back to us if you have doubts.
Yeah. Majority of things we have touched upon now. It has to be
Yeah,
practiced upon. For
yeah. Now
performance,
even
is there
yeah,
also that option where we give where it is in IO stage, in life cycle stage for performance-based
yes, yes,
analysis?
yes. When we are defining the hinges,
Hmm.
your results will be in the form of that,
Okay.
acceptance criteria.
Okay.
We will be having that immediate occupancy,
Hmm.
then uh, loss of safety,
Hmm.
collapse prevention.
Hmm.
Your hinge states will be
Given in that
like
way.
when we have done the design, we had seen a color band over here at the bottom.
Yeah.
So similarly, a color band at the bottom will be visible where the state of that hinge will be shown.
Hmm. Okay.
Okay, say in green it will be say uh, life safety, or
Hmm.
say uh, loss of safety, or say collapse prevention will be in red.
Okay.
Okay, or immediate occupancy will be in
It's
green.
first. Yeah, that
Okay,
one.
yeah, and LOS will be in between, and in red it will be collapse prevention.
Okay.
Okay, so those hint states are there in the post processing. Okay, that you can see.
Hmm.
Okay, as per the hinge rotations, you will get the results,
Hmm.
right?
I guess
So
perform is also for the same thing, the software which is
perform 3D is specifically devoted to nonlinear analysis.
okay.
Okay, like in ETABS, that it is like an add-on.
Hmm.
Okay, we do we do the linear analysis and the designs.
Hmm.
Okay, but perform 3D, if someone is interested in going deep into nonlinear analysis, they should have perform 3D.
Hmm.
Okay, the
Yeah.
that is the best software for nonlinear analysis and performance based design.
Yeah.
We can also do that over here. That is also there, but it is perform 3D is dedicated for
Dedicated
nonlinear.
for.
yeah,
We'll see if some of our research scholars comes up with those kind of problems.
yeah,
So once they go through basic linear, then comes up to hinges, we'll again
yeah.
bother you at that time when those research
Okay.
scholars are working in this direction.
Yeah, yeah. And one more thing, I think I had not shown the
Yeah.
composite design. It is very simple.
Hmm.
They can practice, like students or the researchers, they can practice on their own and see the results and
Okay.
how the program is doing the composite design.
Sure.
Okay. Deck sections also they can practice.
Hmm.
Okay. And,
Shear
I
studs,
think
etc. We can give them.
yeah, shear studs, etc. Also, okay, they can go to the example problems in the manual and go and practice that.
Sure.
Okay, okay. So I think I've
Yeah.
covered everything more or less,
Yeah.
and people have also understood. And I
one
hope they
one thing,
practice.
if that can be done, if any one completed example file you can share where you have created all the load cases, maybe stairs also and numpty also, or if some certain project case file you have, that will help
Mm-hmm.
students a lot to understand, like with all the detailed modeling. We are taken simple geometries, no, for
Yeah,
the
yeah,
understanding purposes. If any one
yeah.
complex project which is completed with all the load cases, with all the detailed models, if that can be provided, that will again help them to see that where they are lacking. If in case you
Okay,
have any previous work done for any kind.
okay. I'll see if that is possible. Okay,
Yeah.
I'll
So
just check.
yeah, so these two
Okay,
requests will be with you. One of this and one previously which I have done. If that peer story whole shear can be seen as in one story displacement when we
yeah.
are defining
Okay,
the shear walls as a peer, so
okay,
that
okay,
whole displacement thing can be seen.
okay, okay.
Okay, and Vish, it was very nice. Like 5 sessions have went so quickly, and we'll be definitely again coming back to you maybe 1 or 2 sessions if students have certain doubts remaining, and maybe after one
No,
month or something.
if there are doubts, you can always
Yeah,
send an email
yeah,
to the admin.
correct.
Okay, to our this CSI
Yes, I agree.
yeah, CSI ESPL email ID.
Yes,
Okay, we'll get on to the doubts
yeah,
clearing as soon as possible.
yeah. So
Okay,
you can maybe mail to me those files if or that procedure if you can come up with, so that will
yeah,
help
yeah.
the students a lot.
Okay, okay,
Okay. Okay. Thank you so much, all the students who have
okay. Then
participated.
okay, thank you.
Thank you,
So
and
we'll
Vish
conclude.
again.
Yeah.
Yeah.
Okay. Okay.
Okay.
Bye.
Okay. Thank you, everyone.